Um, so as advertised, I'm going to try to talk a little bit more about the push forward. Now, so the basic idea, the concept in O'Neill is strongly tied to some kind of picture like this. If you've got a space M, and you've got another space N, and you've got a mapping that goes from here to here like this, F, you can look at a curve, right, a smooth parameterized curve, as we like to, in the domain like this. I could draw a picture like this, right? Call that alpha, right? And then the thing you might not have thought of course, alpha is itself, there's, I don't know, I won't even draw it, but there's a domain, a map, you map from the reals. Oh, fine, I'll draw it. This is the image. Actually, I'm not going to. So, I can't make up my mind. Oh, I know why. It's because I need another color. So, technically speaking, that's from some set of the reals, right? Some domain for alpha like that. And so what happens is you have a point down there, t, and what happens? Alpha puts it up here, like alpha of t, right? That's what a parameterized curve is. In some sense, alpha is this map that glues the line segment up into the space in a curvy way. That's what a parameterization is. So you could also go from here over to here like that. You could take F composed with alpha. F composed with alpha would also give you a path over here, right? And a typical point in the path would be something like F of alpha of t. So you take a path here, and if you have a mapping from M to N, you can move the path over to there like that. That's the first kind of push forward. You can push a path from the domain to the range. But the thing is, if you can do this, you can also transport a velocity vector to the path. And so the velocity vector to the path, usually we look at 0 for the sake of convenience. We assume 0 is somewhere in here in the I. And so there's a tangent here, which we could visualize like that, alpha prime of 0, right? And so there's also going to be f of alpha of 0 is going to be over here somewhere, And then there's a corresponding vector over here, which would be, f composed with alpha prime of 0. And this is what the push forward is. Push forward says, the push forward maps the velocity at 0 to the velocity of the push forward curve at 0. So the push forward, which we use a star for, f star, basically f star of alpha prime of 0 is equal to f composed with alpha prime of 0. This is O'Neill's definition of push forward. Now, maybe I should use a big F instead of a little f everywhere here, because I've tried to get in the habit of using big F for a mapping from Rm to Rn. So if you'll forgive me this slight edit on what I have on the board, I'm going to replace all my little f's with big F's. All right. Set up a trap for myself. Where I used to work, we had these, podiums that were. They had this giant. We called it the umbilicus. The umbilicus of cords. It had like multiple cords that went to the projector and all kinds of other stuff, and it was all wrapped in this like kind of shrink wrappable stuff or whatever. But for whatever reason, they had arranged it so the lectern was here. The umbilicus went to this plug in the wall right here, and then the boards were here. And so like the whole time you're lecturing, you're just like, I'm just like, I felt like sure at some point or another in the semester I was going to fall flat on my face, but I was actually looking forward to it because I felt like it would have improved my course evaluations. I think if you can fall flat on your face while you're teaching, your students will admire it, right? Now, so something I have been on the okay, so what is the tangent space at a point to a manifold, right? So I have advertised two different viewpoints for you so far. The tangent space to a point in a manifold. I said, well, first of all, we could think about it just as like a concrete set of points. That was your homework, essentially. I mean, you've had problems like that. More or less, problem 10 from this homework and the previous one are kind of from this viewpoint. It's what I started with. So one thing you could think of it is just like a concrete subset of Euclidean space. But we also said that that's the same as the derivations at the point P of M. This is like smooth, smooth differential operators, linear and Leibniz, right? So that's actually the viewpoint I try to stick with most often. The tangent space is derivations at a point, right? So when I'm thinking that way, I'll expand a vector how? Like, in this world, I'll write things like VP equals to the sum I equals 1 to n of, V upper I partial xi at the point P. That's from that world, right? But the other, and I write equals here, but really I should have it approximately equal because, I should have, to be honest, these are isomorphisms. There's an isomorphism between viewing it as a concrete set of points. To the set of derivations at a point. And there's also an isomorphism to equivalence classes of curves. At P. Equivalence classes of curves at P? How is that a tangent vector, right? So the explicit isomorphism, guys, I can write it down here. The explicit isomorphism here would be like P comma, the vector V1, V2, Vn, the concrete vector attached to the point P corresponds to this right here, right? What's the equivalence class of curves that corresponds to that vector? Well, in Rn, I could just write it as the equivalence class like P plus T times V1, V2, Vn. You're like, well, what do you mean by that? And I'm going to try not to, I'm just saying this once to get it out of my system, and then I'm hopefully not saying this again. O'Neill hints at this in homework exercises in chapter 1. He's got a problem where he asks you to calculate the derivative, the directional derivative using a line, but then doing the same with a parabola and doing the same with another curve that all have the same velocity vector at 0. The point of that homework exercise is it's nipping at the heels of this equivalence class of curves idea. Let me just give you the definition. Here's the definition. Gamma 1 is equivalent to gamma 2 at P if and only if gamma 1 of 0 equals to gamma 2 of 0 equals to P. All right? So I'm going to give you a definition in Rn. There's a more abstract definition, I suppose. Well, I don't know. Do I need that? I guess this definition works in the manifold. I haven't used coordinates here yet. And what else? Gamma 1 prime of 0 is equal to gamma 2 prime of 0. And, okay, so at this point I'm in trouble with last lecture because I gave a technical meaning for derivative of a curve at a point, right? And I'm completely ignoring that discussion at the moment. Here I'm going full Calc 3 on you. I'm supposing actually that here gamma 1 and gamma 2 are mappings from some subset of the reals to Rn, okay? And here, gamma prime is just defined in the usual way we differentiate space curves. We differentiate component by component by component, you know? So this says two curves are equivalent at P if and only if they both go through 0 at P. They both go through P when you put in 0, and they have matching velocities. That's an equivalence class of curves. You can prove that this is an equivalence relation. Is any curve equivalent to itself? It's kind of stupidly true, right? It has its own, the velocity matches. If the velocity of curve 1 matches the velocity of curve 2, does the velocity of curve 2 match the velocity of curve 1? Yes, because it's defined in terms of equality. And the transitive property also follows because of equality. Like, it's very easy to verify that this is an equivalence relation. And the equivalence class of these curves is what some people would say is a vector. I think that's even weirder than the derivation viewpoint that I've shared with you. But O'Neill uses it to formulate definitions if you really take a look at what he's doing. So let me draw a picture. Here's a point P, right? So the idea of this is that for the vector, let's say, which we can, sort of denote like this, let's say VP, what curves represent that vector? I mean, to start with, you could do like something like this. Whee! This has velocity like that, if that's where 0. I'm assuming 0 for the curve is at P. But you see, you could also do like this. That curve also has the same tangent, the same velocity vector at P. Assuming, of course, we parameterized that curve so that it hits P at 0. But this is not, I mean, there's more, right? Up here, like this guy, and this guy. There's infinitely many curves that go through that point which spit out that velocity vector. Any one of them can be used to characterize the velocity vector, is how some people think of tangent space. Now, in that infinity of curves, there's one very boring one you could use to represent the tangent vector, which would be what? The one straight through the middle of all this, right? Just the line, this guy, right? So if this is gamma 1 and this is gamma 2 and so forth, then I could say the equivalence class of gamma 1 is equal to the equivalence class of gamma 2 is equal to the equivalence class of, well, let's say L, where L of t is equal to P plus t times the vector VP. And if you really take a look at how O'Neill defines things, you'll start seeing that he has composed a function with this quantity right here. So many places, when you look at the formula in O'Neill, you'll notice that he's actually done this. P plus t times a vector in a function. He's picking out that particular representative of the class of curves because it's most easy to think about. But then, of course, there are advantages to the equivalence class of curves viewpoint, namely that the push-forward definition just becomes this. But to be fair, I mean, to be honest, that's not the definition. You have to define the definition for the equivalence class. So really, the definition is this. You have to put brackets around it like so. And then you have to put brackets around here like so. O'Neill is not willing to commit to that because he wants to have his cake and not define it too, because otherwise you end up with this 20-minute spiel about things people don't care about, as is my custom. So anyway, I'm just telling you this because I think if you start to ask deeper questions like why was this the definition, you'll be able to see why if you're aware of this issue, this way of thinking. Anyway, Okay, so got that out of my system. Let me give you an explicit example of push forward. Maybe this will help. We could look at f of x comma y comma z equal to x comma y, just like that. And we could look at a couple different curves just to get a better sense of what's going on here. One thing, we could take the helix, right? Alpha of t equal to, what is it? Cos t, sine t, t. So I'm taking the unit helix, right? And we could try to map that under the mapping f and see where it goes. Where do you think it's going to go? Like, what is f of alpha of t here? So we're going to put x equal to cosine, y equal to sine, z equal to t. So what do we got? We just got cosine t sine t. So due to poor planning on my part, I'm going to draw the action of the mapping f in a vertical sense. I have no regrets, though, because I think it's kind of fun to look at it that way. So down here, what is f composed with alpha look like? What's the image? What's the curve it's parameterizing? It's a what? It's a circle, right? So that just comes down to the unit circle. Well, I mean, I guess I don't know how much of the circle it is until I tell you what the range of parameters is, right? Okay. And let's see here, another example. Let's say beta. And let's let beta be just like a vertical line. Pick a point, any point. Let's say 1, 3 is our point, 1, 3, t. So like that is a vertical line that goes through the point 1, 3. So it's like, it's here somewhere, I guess, right? That's beta. What is f of beta of t? One, 3, yeah. So now we could study the push forward under the function big F of these, of various velocity vectors to these curves, but really just 0 because of the way we set things up. So what's alpha prime of 0? Zero, I think it's 0, 1, 1, right? So if I differentiate cosine, I get minus sine. Differentiate sine, I get cosine. Differentiate t, I get 1. Plug in 0, you get sine of 0, 0. Cosine of 0, 1. Like so. What is f composed with alpha prime of 0? Yeah, it's just 0, 1, right? Very good. Differentiating that and plugging in 0. So what this shows is that the push forward of 0, 1, 1 at the point P, which the point P here was this point. Alpha of 0 here is 1, 0, 0. Yeah. So the push forward of this at the point P is equal to 0, 1. And where is 0, 1 at? This point is f of P, right? And that happens to be 1, 0. So the push forward took this vector in 3 dimensions over to this other vector in 2 dimensions, like so. In contrast, what's the push forward of 0, 0, 1? So you notice that beta prime of 0 is 0, 0, 1, right? And f composed with beta prime of 0 is, well, 0. Because f composed with beta is a constant map. So you can differentiate it all day long. All you get is 0. So this is 0. I mean, to be fair, it's 0 at the point f of p in R2. Tangent space to R2 can be fuzzy. So for this map, the push forward kind of behaves the same as the map itself, right? It just projects out the z dimension. If the map has like a formula which has squares and nonlinear features to it, it can take a line in the domain and make it into a curve in the domain, in the range, and all kinds of interesting things can happen. Yep. Oh, okay. So, excuse me. Now, what's the Jacobian for this one? Remember we said partial f, partial x, partial f, partial y, partial f, partial z. And so this is, f is a mapping from R3 to R2. So I told you that will make the Jacobian 2 by 3. 2 by 3. So what we have here is 1, 0, 0, 1, 0, 0. That's the Jacobian matrix in this case. And if you take that matrix, right, and you multiply the vectors that we had, 0, 1, 1, or 0, 0, 1, times that matrix, you'll get the same result that we got by composing the curves and differentiating. So the main thing I say in this section is just like, a lot of it's notational. I say something along the lines of, if f is a mapping from R with coordinates x1, well, let's say x1, x2, x3, right? And I use the notation y1 and y2 for the coordinates in the domain, like for this example. Then the things I just worked through, let me rewrite them in the differential in the partial derivative notation. What these calculations indicate is that the push forward of, well, partial x2 at the point P plus partial x3 at the point P, it's equal to partial y2 at the point f of P. That's this statement. So this in differential notation is the sum of those two derivatives. And in the y1, y2 notation, that I would denote by partial y2 at f of P. Like this one says that the push forward of partial x3 of P is 0. So that's all. We'll come back and use this later, and when we use it later, it'll make more sense in the context in which we use it. There are, because we're studying spaces and we have maps between spaces, and having a push forward allows us to transport vectors from one space to another and to say things from one space to another on the basis of that comparison. Finally, an apology for the homework. Problem 1, like, that did not make sense as it was originally stated. And thank you, Audric, for working ahead a little bit. I hope you, did anybody else waste a bunch of time on the first one with the, no? Okay, good. Yay for procrastination, right? I should mention a little bit more about how we can judge whether or not a parameterization is reasonable. See, because I just mentioned to you, so this is the big idea. We've got some domain, right, which is a subset of whatever dimension. So suppose we're parameterizing a k-dimensional space. So that means that the parameter domain is some subset of our k, right? K is equal to 1 for a curve. K is equal to 2 for a surface. K is equal to 3 for a volume. K is equal to 4 for a 4 volume, and so forth. Like, you have as many parameters as you have dimension in the space you're trying to parameterize, right? And for that to be a reasonable statement, whatever map, I often find myself using big X for the parameterization. I did that in your homework, right? I use big X for a lot of things, though, so don't read too much into it, largely speaking. But this will give us some kind of whatever blob up here in, let's say, Rn. And I usually think n greater than or equal to k, right? So we can take a surface in 3 dimensions. We take a 2-dimensional domain, and the parameterization map pastes it up in R3 as a surface, right? For example. Now, in order for it to be a parameterization, what we need is that for every point in the domain of the parameterization, this map has to be invertible. If you can't invert the map, it's not really an honest parameterization, because there should be a one-to-one correspondence between this set D and also, the thing it's describing M. So this needs to be invertible. Or at least it needs to be mostly invertible for our purposes. Okay? In Calculus 3, we work with cylindrical coordinates and spherical coordinates. Those are mostly invertible. But they're not, strictly speaking, invertible, right? You give me a point that has standard angle pi over 4. Somebody else could tell you, no, that's not angle pi over 4. That's angle pi over 4 plus 2 pi, or maybe it's angle 3, 3 pi over 2. Or somebody else would say, no, that's angle minus pi over 2, standard angle, right? I mean, there's a degeneracy in angle that can't be, you can't get rid of that and keep all of R3. There's some place where the angle doubles up, right? There's an origin where, what's the angle of the origin? 0? So yes, other people's would, you can make it whatever you want. That's the problem, is like angle is not uniquely specified by the equations which define spherical coordinates don't force any particular angle at the origin. And if you did make it 0, then you have a problem of continuity also, because infinitely close to the origin, you have angles of whatever you want, right? So like, we can't just ad hoc give it a value, because then the infinity of other values that surround the origin, I mean, you could, but then it would be discontinuous. I mean, things you'd want to say would break down. But that said, those are examples of this sort of map. My point is that with the cylindrical or the spherical coordinates, they're mostly okay. It's just there's like a defect at a point or along some line or plane or something, but the most of our 3, they're invertible. All right? So we do, what I'm trying to say is, in practice, we weaken this condition of invertibility as it suits our fancy. It suits our fancy in applications. Unfortunately, in my original statement of problem 10, my parameterization was not invertible. The point I picked and the formulas I gave you gave us a velocity vector which was 0. And that's symptomatic of a lack of invertibility at that point. So here's a theorem. If partial x, partial u1, partial x, partial u2, partial x, partial uk are linearly independent, then x is 1-to-1 near linearly independent at, let's say, a point. I need some label here. I don't know, u vector sub naught. There we go. Then x is 1-to-1 near u sub naught. Now here, I'm assuming that the mapping x is differentiable and has a continuous derivative. So it's once continuously differentiable. If I have that much data, if I have linear independence of all these, then I can invert the map. I didn't have that for your homework problem originally because partial x, if you have 0, it's definitely not linearly independent. Maybe it's almost helpful to have an example of where this doesn't work. So check this out. If I tried to do x of, let's say, u, I'll keep with my current notation, u1, u2 equal to u1 plus u2, and then 2u1 plus 2u2, right, like that. And fine, we can put here. I'll slap a 3 on here, just for good measure. So on the surface of things, it looks like it might parameterize a surface. But this would not be a parameterization of a surface in R3. Why? Let's see here. Well, that's not a problem. I mean, we can. Uh-oh. Still okay? Lost power there for a second. We have z equals to 3, right? Yeah. Let me try to convince you that this is not a surface. Check this out. So z equals to 3, right? And I'm going to use x, y, z coordinates for the range, if that's okay. Z equals to 3. This is x. This is y. How are x and y related? Yeah, y is equal to what? 2x, right? So what's this? When we have y equals to 2x and z equals to 3 in 3 dimensions, what is that? Is that a surface? Right. So here's z equals to 3. That's a plane, right? And what's the other one look like? Y equal to 2x, yeah, straight line. So it's like this, right? But it's also like this. I can't draw where they. I mean, it's a plane. It's a vertical plane, actually, right? And it intersects the plane z equals to 3. I should have used a different color. Right there. There is a line of intersection, right? So the image of x of R2, is a line. It's this line, right? If you want, I can give its parameterization. Here's the parameterization of the line. L of t equal to apparently t, 2t, 3. There you go. There's the parameterization of the line. It stays in the z equals 3 plane, and it stays in the y equal 2x plane. But it's a line. So this is definitely not a reasonable parameterization. Now, how does it fail to satisfy this theorem right here? Well, partial x partial u1 is what? What's partial x partial u2 equal to in this case? So yeah, these are, just to be clear, these are 3-component vectors, right? Because of my sneaky notation. Yeah, 1, oh, you say 1, 2, right? 1, 2, 0. And how about partial u2? 1, 2, 0. Are these linearly independent? Definitely not, right? So, in fact, this is a condition we're going to need in a later chapter when we define surface in R3. We're going to insist that the mapping, the so-called patch or whatever you want to call it, satisfies a so-called regularity condition. The regularity condition is essentially that, well, it can be imposed by saying that the partial derivatives with respect to the parameter variables give you linearly independent partial velocities. You could also characterize that condition in terms of a push forward. It's probably, I think it's entirely equivalent to say that the push forward of the coordinate velocity, of the push forward of the coordinate, good grief. If we looked at like x push forward, partial u, I'll use upper I because I feel guilty about it, partial ui at my stupid point u naught. So those would give you vectors up to the tangent space of M, and those would be linearly independent if the mapping is regular. It's like another way to look at it, but anyway, I'm digressing. So anyway, I wanted to mention that. Maybe that helps you understand a little bit more about what a parameterization is or what it's not. But I also said it was going to help us understand the Jacobian a little bit, right? Let me try to explain that, what I mean by that. All right, so we okay? Okay, so if you don't mind, I'm going to engage in another edit. You don't have to change it where it was in your notes before, just for the sake of what we're doing now. Okay, so here's the thing. What's the linearization? Linearization of f at u naught. What it is f of, let's say, x. I'm going to put a vector to emphasize it's a vector. It's not a single variable, but a vector of variables. F of x is equal to f of, now I'm all of a sudden putting vectors over f because I'm an idiot. f of x, f of u naught, f of that listen to me, specific point. My kids don't hear this, and that'll be the end of it. The Jacobian of f at the point in question times x minus that point, which I really wish I had called u x naught, but oh, whatever. Maybe I should make, well, I will. All right, I can't help myself. I'm going to make that a u. It's bothering me because I'm using u for the variable in the domain here at the moment. So probably should put u's there to be more, reasonable. So what does it mean? Now, this is not equals, right? This is what? This is approximately true. What we have on the the right-hand side here is this is the linearization, which I sometimes call like L sub f at u naught or whatever, all right? That's the linearization of the function. So guys, what does it mean to be able to find the inverse? Let me take it back down a notch here. Suppose we have f of x equal to the square root of, 1 minus x. And I say, okay, go find the inverse function. What do you do? Right, so I just set it equal to y, and I solve for x. So square both sides, I get 1 minus x equal to y squared. Solve for x, I get x equal to 1 minus y squared. So f inverse of y is equal to 1 minus y squared. They taught you to flip the x and y at the start of the calculation because they don't believe that you have the intellectual capacity to look at an inverse function of a letter other than x. This is why we teach children to switch the x and the y at the start of the inverse calculation, because we don't want to find ourselves writing function of y at the end. If you're willing to write function of y, you don't have to switch the x and the y, you just solve for x. I like this because, truth be told, there is a different variable going into the inverse function and the function. Right? This is more apparent if you do something like, say, f of x equal to e to the x. That's good for any real x, right? Set that equal to y. Solve for x. Right? Natural log of y. F inverse of y equals to log of y. This is good for all x in the reals, right? This is not for all y. This is only for what? For positive y, because the range of the function is the domain of the inverse function, and vice versa. So I personally see a great advantage in using a different letter for the domain, for the function versus the inverse. But you also sometimes graph them both on the same axis, and then you need to figure out what f inverse of x is for making a graph of both of them at the same time. So you can't get away, you can't have everything. Okay, now that we've taken that trip down memory lane, find me the inverse of f. Well, the next best thing is to find the inverse of the linearization of f. After all, that's really close to f, close to the point. So it's not unreasonable to suppose that to a good approximation, if we can solve this for, let's say, y, solve that for u. In this case, I got to solve for u since u is like my x. Can you solve for u? So solving for u here, and by the way, for this to make sense, I need k equals to n. Otherwise, I got to say a bunch more stuff. But I want to say k equals to n to keep it simple enough, because otherwise, if k is not equal to n, this is not a square matrix. But if k is equal to n, then the Jacobian matrix is a square matrix. So you said subtract from both sides. I agree. So we get the Jacobian of f. I'm going to just write u minus u naught is equal to y minus f of u naught. Great. And if that's a matrix, how do we get rid of it? We do what? We multiply by the inverse matrix, right? So multiply by the inverse Jacobian. And then add u naught. So there you go. U equal to u naught plus the inverse Jacobian of f, y minus f of u naught. That should be approximately equal to f inverse of u, of y rather. This is actually more or less the proof of the inverse function theorem, or the inverse mapping theorem. It's actually essentially what I just showed you. We can linearize the function. Now, the truth be told is that when we linearize the function, there's an error term. All right? And when you go through this algebra I just went through, you also have to deal with the error term. And then the hard part of the proof is showing that that error term goes to 0 in the appropriate way to show you that the inverse exists and such. Actually, well, there's something called a contraction mapping argument that you use, and it's more involved. But this is the heart of the argument is just this. And in order for us to find the formula for the inverse function, essentially we needed the condition what? The Jacobian of f is invertible. So that means that the determinant of the Jacobian of f is what? Is non-zero, right? But what's the Jacobian of f? It's partial f partial u1, partial f partial u2, and so forth and so on. So that's only going to be non-zero if all of these guys are linearly independent. That's linear algebra, right? The matrix is only invertible if its columns are linearly independent. If there's any linear dependence amongst the columns of a matrix, it has 0 determinant. Now, the theorem doesn't say that if the coordinate velocities are linearly dependent, then it's not invertible, right? It's actually silent as to what happens when the condition is not met. But odds are that it's not invertible when that condition is not met. To give you an example of kind of like where the condition is not met and yet it's invertible, the cubic functions is that kind of example. Y equals x cubed has a derivative which is 0 at 0, and yet the function is still invertible at 0, right? Because it's just 0 at that one point, you know? But anyway, and then it turns out that something similar can be said when n is not equal, when n is larger than k. This still continues to be true, but we can't take the determinant anymore of the partial velocities when the target space is larger than the domain. Like in this example I gave you over here, we couldn't have taken the determinant of like what would you even mean determinant of where were they? I mean, how would you take the determinant of this? What's that even mean, you know? Can you do that? Is that allowed? I mean, it's no, right? So, nevertheless, the theorem continues to be true, even though the determinant doesn't make sense past the case that you have equal dimension of parameter space and the place you're mapping to. So, now, where we're mostly using this is just for our definition of curve. We want a regular curve. Regular curve is one where the velocity is non-zero along the whole domain. That means that the curve is actually one-dimensional. If you had velocity of the curve drop to 0, maybe it's not really the kind of curve we want to think about. It's a stupid curve. This is a stupid curve, right? It's a mapping from the reals to R2, which is always the 0.13. Like, depending on how you want to cut the definitions of things, you may or may not say this is a curve, right? depending on which book you're looking at, this may or may not actually be a curve. At the very least, it's pathological, you know. But we can avoid that kind of thing happening by assuming our curve is regular. Okay, so listen, that is all I have to say. Probably I said too much. I said I wasn't going to spend an hour. I've spent exactly an hour. Let's take a little break, if that's okay with you guys.